Okay, let's start. Thank you, everybody. And yeah, what we are going to do is just mainly work a little bit with Circom. We are going to do well, we're going to try to do a full project, trying from the beginning, and we were going to try to code and see very much how we work with this zero knowledge. Here, just a little disclaimer. The project that we're doing here is just an example. Probably there are things that could be done better, that can be done with much more performance. So do not take it as anything serious. Just an example, just to learn Circom and to learn the zero knowledge. So let's start. The project that we want to build, let me share the screen. That's the first thing that I should do. Share the screen. Okay. Okay. I hope everybody see my screen. It's a bigger screen, so maybe the people see it. I'm going to try to do it bigger. Okay. So the main thing that we are going to build is a project that tries to prove that you were somewhere at some place. So what the project will consist? Well, the project will have like 3 actors. Okay. The first, we are going to suppose we have, for example, a trust GPS, or maybe some oracle or somebody that states that somebody tells you where you are at some time. Imagine that you have a trusted hardware that you can ask them where you are, and they makes you approve. This hardware will just create a packet. Let me just see if I can say that here. So we'll create a packet. It will create here. It will create a packet that contains, of course, a location, so a latitude, a longitude, maybe a timestamp, an ID, maybe the serial number of the trusted hardware or the ID of who you are or the oracle, okay? And all these will be signed. So all this packet will have a signature. Okay. So yeah, we have, maybe we can collect a lot of these attestations, a lot of these proofs that the trusted hardware have, and this is already in my possession. But maybe later I want to prove you that I've been at some point in the time, maybe 3 days ago, I was very close to Barcelona, but I don't want to tell you the exact time when I was to Barcelona and exactly how close I were. So I don't want to reveal you the full latitude, the full latitude and longitude, the exact latitude. I want just to tell you that maybe that you are, so here is the globe, okay? So I want to tell you here is a point, and I want to tell you that you were just close inside this circle. So you are close to this point, but you don't want to know, if you are here, if you were here, or if you were here, if you were here, or even if I was, for example, in the morning, in the afternoon, maybe with a window with the time, okay? So I want to generate, I want to create a proof based on this data. So I need to have this signature. The signature here is important, okay? So the verifier knows the public key of the trusted hardware, okay? So, and I want to so they trust the public hardware. This is what we are assuming, but I want to prove that I'm close to there. Okay. So the first step will be to generate this attestation. The second step will be to generate a proof. Okay, that you have some of these points, and the proof. If we see, in order to generate the proof, we need like a reference. So we need to assess, for example, one thing is exactly what the point I want to prove that I were close to. So I will need, for the proof, I will need another latitude and another longitude that should be close to the one that that we are stating. Maybe I want to, for example, a time window, maybe a time from and a time to. Okay, and I want also to generate a distance. So how much close do you want to prove? Maybe this can be 10 kilometers, can be 100 kilometers, can be, I want to prove maybe that I was in Europe, so I can put a set point in the middle of Europe and I can say that there is, I don't know, 3,000 kilometers around. And this will prove that I were in Europe, for example. Or it can be very close. It can be I was in some place, and it can be like, I don't know, 100 meters, maybe a zone or a place. So this distance is important because I want to prove how close, I want to prove that I was inside the circle. But I repeat, I don't want to verify, I don't want to reveal this, I don't want to reveal the exact location and the exact time stamp of the location. I just want to prove that this fulfills, okay? And of course, the verifier will take exactly the same reference plus the proof. Of course, it will not take the attestation, and it will prove that, and it will verify that this is, that the attestation will verify that this proof is okay. Okay, so this is very much the project that I want to do. So let's start. Let's do it. Okay. So the first of all, I'm going to do I'm going to go very fast, and I'm going to do a little UI in order to show that. And mainly I'm going to put and paste. Well, let's just create the project. I don't know if you see here. Let's call this zk location. And just create a project. Okay, just create the project. Let's create, for example, a directory where we are going to create the HTML, and can be public. Okay, let's open this with let's just okay, so we have it here. Here is the content, new file. Let's call index.html. Okay, here is some boilerplate. I'm just cut and paste the one that I have it here just to go fast. And we'll go through over it. So, well, this is not. Moment. Okay, so here is, well, this is a normal HTML, nothing important here. Just let me just see this HTML, because this is very much what we have seen now. So let's just go see the public. Let's run a server, and I start a server here. I need to save it. Here it is. Let me just do it a little bigger. So mainly that's nothing here, but here is what I create is like the This is the interface for the positioning system. We are going to simulate an attestation, approved GPS, okay, a trusted hardware, a trusted GPS that will just generate this. Will generate, as I told you, an identification, timestamp, a latitude, a longitude, and would just generate an attestation, a set of data that mainly includes this information, sign it. Okay. Then the prover. What we want to prove? Of course, we want to prove of course, to prove that, we need to have the certification generated before. Okay, we need the time window. So from and to the time window that we want to prove that we were at that specific place, the reference place that we were close to, and how much close we want to prove. In this case, it's 10 kilometers, so we can set up to everything. So with this, we will generate a proof. Okay, and at the end, we will verify that. What we need that to verify? Look, we just need the proof, that the proof is a zero-knowledge proof. This proof do not reveal any information, just a proof, and it proves that this identifier was at this location between this time and this time, but without revealing the exact location you want. And this verification will just returns true or false. Okay? So this is, we have the interface. I think it's good to write the interface because we know what we are building now. And now let's start. Let's go to the first part. Okay, the first part is going to be to write the packet the packet position. Okay, so this attestation. Okay, so this is very easy. We, of course, the first thing is that we cannot use normal signatures. We need to use the baby job. We are using EDSA signatures. So in order to do that, we are using Circom0.5. Circom0.5 is it's a library that mainly that includes a lot of circuits to work with zero knowledge, but also includes a set of JavaScript tools in order to, for example, to sign not in the circuit, but to sign in the browser and so on. So let's create that. Okay. So in this case, I'm going to create. Let's create here a new folder. Let's call it source, and inside the source, let's call a new file, and this is going to be the signer. Okay, so the signer.js, let's see how it looks like. Again, I'm going to do a little bit cut and paste, but we'll go through the code there. So the code signer, if you go to the signer, okay, let's see. This is a signer. Okay, so here we define a packet. A packet is going to be included inside a field in a 256 bits. Actually, it's not 256. It's like 253 bits. Is the order, a number that's inside. It's an element of the inside the order of the curve of the baby job curve. Okay, so this is the prime field. So let's see. Well, here we require the big numbers. Here we have some. We here include from Circom some information, some helpers. EDSA is what actually is all the library that helps us to sign things. Okay, Little Indian into buffer, and it converts a Little Indian to buffer just for the result to put it in a normal buffer, in a normal hexadecimal number. Okay, and well, that's it. And sign Poseidon actually is not used, so we can remove it from here. Okay, so so here is the proving key. We need to generate here. I hard code a random. This is a bad practice. Do not do that. This is this for testing purposes. I just hard coded here in the code private key. This is wrong practice, but in order to just move forward, I just put it here. So I just create this private key, and I generate the public. I generate it here from this private key with EDSA. You can generate the public key. Okay. So and from this public key, I can here is what I do. I sync. So the sign here is what the actual work does. Okay. So here we have the sign. Let me just do it a little bigger, maybe. The sign, it takes the identifier, it takes the timestamp, it takes the latitude, it takes the longitude. Okay, it packs here the first lines mainly. It packs them all together, here it packs them all together in a field element, okay, in a number, okay, and then we just sign this number with the private key, okay, and the result we'll just put it in a buffer, okay. That's mainly what we are doing, okay. And at the end, we just return this hexadecimal of this buffer. So this generates mainly generates the proof, okay. And well, we also export here the public key, so we can know this signer also exports which is the public key. So let's see, this is like a closed things, okay. So that's mainly nothing fancy here. Just we are assigning here. Maybe the only interesting thing is how we code floating points, because here we are always working with integer numbers, but what happens when we want to work with floating points inside the snar? Well, we need some kind of codification, okay? We can use some normal floating point codification, like an exponent, this sign bit or whatever. I just created one that it works okay, and let's see how this is done. So in order to do that, I should go maybe here, and yeah, here is mainly what it does. Well, I just take 56 bits numbers. I just take 56 bits. The first 25 bits, so the less significant 25 bits are just the mantissa. The most significant bit is the sign, and it's a fixed exponent. So in this case, I just take 2 to the 32 exponents. That's what I'm working. Of course, this can be parametric, and this is one of the good things of Circom, is that, for example, I can write a full library that works in floating points, and maybe the size of the exponent can be parametric. So I do not have to rewrite everything. I just have this template that generates circuits that works with different precision, and I can reuse them. And that's one of the interesting things, for example, of Circom. So, well, mainly what it does, this function that we see here, float to int, mainly if we just take a look at float to int, well, I just create these utils where it has all these things, so new file, utils.js. So let's just cut and paste the utils.js so we can see all these functions, how it works. Here I have a bunch of functions, but float to int, so mainly, of course, here I already take the number that I want to encode to this in this case is to a number, okay. So and the n is how big, in this case would be 56, and the e is the exponent. In this case, it's going to be 28. So here is already, you see this flexibility of doing the things very well, much more for free. And then e, I just take 56 at 32 by default, and well, I just check it if the e is negative. If it's negative, I just save it, and I just create the positive part. And the positive part, just mainly, I just take this number and just convert it to a normal integer. And then if it's integer, I just set the sign. Set the sign, you just put the next bit. So here I have a
Jordi.
Yes?
Sorry to interrupt you, but can you increase the font a little bit?
Yes. It works better now. Maybe I can do it.
Is it okay now, guys? Because somebody's writing in the chat, they can't see it. Okay, cool. All right. you can speak up if you want, like during the talk as well, if something happens.
All right. Please interrupt me if you have any doubt, or maybe I'm doing okay. So. Okay. Well, you see here is the normal codification, and that there's a normal codification that I'm doing here. Okay. So of course, so here I encode the latitude, the longitude, and the timestamps are just integers. So I just take 32 integers. So here is how the field lasts. So the low 56 bits are the longitude. The next 56 bits of the most significant bits are the latitude. Then 32 bits of timestamp, and then 48 bits of an identifier, just a normal integer. So we put them all together to a field element, and we just sign them. Okay, so let's just do that. In order to work that, well, we need to do some tricky things. What I do here is, well, there are many ways to do this, but one easy way to do, and oh yeah, here I mess it up. Okay, just go online here, just mess it up here. Well, one way to do this is here in the public. What I do, for example, is just I create a main. I just create a main main.js, okay, and this main.js. Just let me copy and paste this. It's a very easy one, but just what it just does is just publish an object that's in this case one is the distance prover in this case, and just put this the signer. In this case, we need just only the signer. We have also the prover and the verifier already, but this is mainly the signer. Okay, so I'm just going to comment maybe here so that it doesn't disturb here. Okay. And with this, everything should be ready. Let me just see if everything is ready. So what I do here is just use Browserify. So I can just do public, just in order to convert to a bundle so that it can be seen in the, so we can load in the normal web page. So here what I do is just Browserify. I mainly want to do main.js, and the output is going to be bundle. So this is mainly what it does for the people that don't know JavaScript. It takes all the dependencies, all the requires, and everything. It packs all together so that you can run it in the browser. So here's bundle.js. Okay, here is, I think, well, this is going to be some, well, it works. Okay, so now, if we go to the HTML, just to see, just go to the HTML. Well, at the beginning, I just set up here the init. I just put normal standard all the values to the fields. Just put a default value here. Okay. So here I have just a normal form that's assigned. Here I have all the buttons and so on. I have a button that's that just says on click, just pack and sign. And if we go to the pack and sign, so mainly just create a form, just calls the distance prover dot sign with the identifier, the timestamp, the latitude, longitude taken from the take it from the UI. Okay, so here
you confidentiality.
Sorry, I couldn't hear you. Can you repeat? Okay, I can hear, but anyway, I continue. I didn't understand what you say. Okay, so so here I just call this distance prover, and then I just put the result in the signet packet result. So let's see if this works. Okay, so see if we go to the here, just well, I need to reload this. There is some error here. Let me see. Prover.sign is not a function. Prover.sign is not a function. Let me see. Looks like it doesn't main signer require source signer. Oh, what happened here? Oh, I messed it up. Well, I need to include Circom0.5, no problem. See if it takes all the video and all that stuff. It takes a while to download. Come on. Hmm? No. What happened here? Hmm? Why it doesn't load? It takes too much. Well, let's move forward. Let's try it later. So let me just go to the original repository. So this is the one that should work. Hello? Can you hear me?
Yes.
Okay. So let's just back and sign. Here it just generates, as you see, well, this is what should happen in the other side. It just generates this. As you can see here, here we have the, well, we have all the mainly the first is all this is a little Indian. So here is the node, the code that we want to generate. These remaining zeros is because there's 256 bits and we are using some them of less. And this is mainly the signature. All this is the signature. It takes 3 field elements, a point, mainly is a point and a scalar. Okay, so this is the everything is embedded here. Okay, so once we have the signature, then we need to go mainly to the main work. That's mainly to write the Circom, to write to write the circuit. So let's go directly to writing the circuit. See, here we go, and we just location, just generate one. Just let me just do it from outside. Circuits. Okay. And the main circuit that we are going to build, and here I'm going to put it all together. And we are going to do a top-down implementation here. That's the best way to do work in Circom. So the first one that we are going to build is well, let's see, the first one that we are going to build is the one that's going to be called, I'm going to call it here, I'm going to keep the same name that they had before. DistanceProver.mine. Okay. So let's just let's go create another one, new file. Distance prover.main. Well, let's just go to the first to the code to the distance prover. Distance prover. Let me just cut and paste from here. Let's see what the distance prover does. Okay. So here is a normal program on Circom. See, this is a template. It's a template that has two parameters. In this case, is generic. This should be generic for for the sides of the floating point and the E. Probably in this case would be make more sense just to remove N and E. Okay, but here is just a parametric part. Designing Circom circuits is very much like designing electronics. So mainly what you're just creating, like this is like the first component, and then we are in the first component we are putting more components, and we connect those components. And each of these subcomponents we put more subcomponents, and we connect these subcomponents. So we are doing a bottom top-down design. Okay. So what have here? Well, here is we have a reference. A reference mainly is a byte. Here is the prover is, this is a private, well, this is, so here we take the reference mainly, it's a byte that packs the time window, the reference distance, so the window that we want to prove, the distance that we want to prove, and so the time, the window, and the distance. Okay, and this is packed together, so it's a single number. Okay, but each of the bits of this number have different meaning. Okay, but in the input of the circuit, this is just a single input. Okay, we pass also what would be the position. The position again is another number. You can see it here in the next lines in line 20. Here is again the packet. This is actually what's signed. Okay, so we see the timestamp, the position, and the identifier, or everything, all that packet in this number. So this is the other input. Then we have R8, R8, and S. These three numbers are the signature, the one that was generated before. And then we have an output. Here you see that the output is public. Okay, so in this case we have one public input and one public output. One public input is the reference because we want to prove something, and this something that we want to prove in this case is we want to prove that we are close to some city. So that means that this, if we need to tell exactly what we want to prove. We don't want to reveal the exact position. That's why the position is private. Okay, but we need to know what exactly what we are proving. Okay, so, and of course we also prove that we also give the identifier as public, because we may want to prove. So we want to prove that us as our identifier that we're there, no, maybe not somebody else. So that's important also to put this. The outputs are always public in Circom. Okay, so okay, let's see what it does. Well, here we have num2 bits. This is a component that mainly what it takes, it's have a single input, which is a field element. And the result is, in this case, is all this 56 plus 56 plus 56 plus 32. In this case, 231 outputs. Each one is a field element, but if this field element is guaranteed that can only be binary, can only be 0 or 1. And this is the composition of this field element in a binary, in binary fields, in binary elements. Okay, so mainly these explosions. So it parses this reference, okay, and it generates a lot of the outputs. Okay, we explode also the same with the position. Okay, so the first thing is we compute the identifier. Okay, we just explode that, and then we just take the specific 48 bits that are from 144 to 192. Okay, and we just send them to the output. Here you see this arrow. In Circom, this double arrow is very important, because here what we are doing is we are doing two things. We are assigning, okay, so we are telling how we are computing the witness, but we are also generating a constraint. In this case, we are also generating a constraint that this must be equal to this. So the nice thing of Circom is that when you are using this arrow, you are safe. You are safe. So have this, if you are using double arrows, you are safe by construction because you are assigning something and you are forcing that. You are also creating a constraint that happens. So while you are using, I would say that in Circom, while you are using double arrows and you are using, let's say, audited components, at least you have the warranty that you are not going to forget any constraint. That's one of the most difficult mistakes so it's the most typical mistakes that you may do when you are building circuits on that. So here is just, we are just connecting, you are assigning, this is like in electronics, we are just putting a wire between, in this case is, well, the output of this component to the input of this component. Here you see that reference, we can take in the reference, is the input, we are connecting to these components. Mainly you see that what we are doing is just connecting the pieces together. Okay, so we have these two components, and then we reconstruct. So this is this bit to num is the opposite of the num to bit. So we are creating from 48 inputs in this case. We are just creating a single field that's guaranteed to have the binary, and with all the constraints that are inside. Okay, and this is used in here in the BT5. This is included from Circom. Okay, so this is a BT5. This is already done for you. Okay, so we compute that and we put it in the output. This is the easy part. Okay, then we have another component that we need to write, but we are already created it just say that it's there. This component mainly has as an input have 2 positions. So the latitude 1, longitude 1, and latitude 2, longitude 2 have a distance, okay, and returns a bit, returns a field element that can be 0 or 1. It's going to be 1 if these 2 points are close enough. They are one is so the both are if these 2 points are the distance between 2 points are bigger than the distance input, then this output is near is going to be 0. Okay, so what we are doing here, check here. So we are putting this triple equal. Triple equal in Circom means a constraint. So we are forcing that is near, so that the output of this is 1. So we are forced. So if we are generating this proof, so if we are running this proof, that here we have a constraint. So this proof, that's what actually we want to prove, that this distance is there. Okay, so that this distance is close enough, so that this fulfills this component also fulfills. What else we want to do? Well, we want to check the timestamp, the window. Again, here we have a we have a here for doing this. We have here if we go here to line 63, we have already a component that's less than. And the less than, it's a very simple component. It takes 2 inputs. In this case, they are not binary. They are just normal fields. And it returns 1 if the first is less than the other. Okay, and returns 0 if not. Okay, so that's a single comparator. But this is a component. It's it's quite complex component, but it's already in the library of Circom. Okay, so we just use them. So this less than, we are using this, and well, this input requires that the two inputs be constructed. So it does not accept binary; it accepts a full field. So we have the bits to nums. We just construct them. Okay, so we construct them, and then the output of this timestamp num, timestamp from num, timestamp to num, we put them to the comparator. Okay, so and we do the same for the comparator from and from the comparator to. Okay, so we have actually the timestamp that's signed, that's going to be the private, and then we have this reference, the reference, the from and the to on the reference that actually are the ones that are going to be public. So we want that the time from is less than the current timestamp, and the current timestamp is less than so that means that's in the window. Okay, and finally, we need to prove. We also need to check. We need to verify that the signature is valid. So here we are just instantiating EDDSA. This is also part of the library, of the Circom0.5 library. That's just checks that the verifier is valid. Okay, so you see here the inputs of this EDDSA. Mainly what you need to pass them is the well, enable. That means that you can disable the signature, but we force this to be 1. So we force this that this component is enabled. You see the things that how are getting close. People that knows a little bit about electronics, now designing zkSummit circuits is very much like designing electronics. Have a lot of common things. So that's a cool part. So another thing is we need to verify is the public key of the signature. In this case, this hard code here, the same way that we hard coded everything, but this is the public key. And here is just the input. This is the signature. So this is just, and of course the message. The message in this case is the position. The position, remember that's all this packet that holds the latitude, longitude, the timestamp, and the identifier. So that's mainly how we sing. Of course, well, this is, again, there are a lot of things that needs to be taken account if you want to put that in a real example. But you can see here how easy it is to write, you know, the full circuit in Circom. So mainly, we just divided the problem, and most of the projects, most of the problems here that most of the, well, you see most of the components here are well, are already implemented, you know, comparators, bin to nums, num to bits, packing, unpacking, the signature. So we have almost most of the work done from the Circom0.5. What we do not have, well, we do not have the is-near, okay? The is-near needs to compute this distance, and also it needs to work also, for example, with floating points. Well, it didn't exist before now, okay? So in this, we just created a little bit of libraries that work with floating points, okay? So here we have a set of tools that we have to wrote for this specific example, but can be reused, okay? And this is all the floating point management, okay? So for the floating point management, mainly we need two functions. Mainly we need to add and to multiply, okay? So let's create this float add and float multiply, okay? So this new field, let's go to the float. Float add.circom. Okay, let's see how this float add would look like. This is a more float add, okay? So, well, it just takes, well, yeah, this is, okay, well, this is probably not the best example. Let's go, well, let's do it. Here we have N and E. N and E is, as you know, is this how big is the floating point, and E is the exponent, is a fixed exponent floating point. So it's not floating point, it's really more a fixed point library, okay? It's just like float, but it's not, it's a decimal maybe, yeah? Number of operators here is, well, this is how many, this is a generic library. So this is actually generates another, so you can add 2 numbers, 3 numbers, 4 numbers, n numbers. So how many operands do you have? In this case, is n operands, okay? So for this example, imagine that n ops is 2. You want to add 2 numbers, okay? But it could be v3, it could be v4. And in order to write it is very easy. And then an offset is, okay, we can also add like a constant. So it's another that you can add 2 numbers, but you know, almost, and this constant is, this is very much for free. So you can add 2 numbers, 3 numbers, 4 numbers, and a constant. So how we do that? Okay, well, let's go a little bit about that. Let's go, this is our just, well, this is the input output, this is our variables that we will see here. So let's start here in line 13, okay? So here, in this from line 13 to line 26, well, we go to all operands, okay? And mainly what we do is we convert all the operands that the inputs are in binary. You see that, and it was in this. So mainly we're here, we are converting from binary to field. Actually, all this could be with the component that we have seen before, the bits to num. Okay, but I just put it here more longer, just that you can see a little bit how it looks like. Okay, so mainly here is of course a variable, and we are building constraints. We want to at the end to let me just go to the report to the one moment. So mainly what we want to build is, we want to convert. So mainly what we want to build is a constraint that says out is equal to the x0 times 2 to the 0 plus x1 2 to the 1 plus until x n 2 to the n minus 1. Let's put here minus 1. Okay, so I want to build this constraint. Okay, that's mainly what I want to build. Okay, so what I'm doing, I just create a variable in this case that's a linear combination, and I'm adding each of these parts. So if we go to the here. So the linear combination, well, we start with offset. To this, we add the offset. And here, for each, well, here is, let's go here inside the loop. Okay. So we start with 0. Okay. And here we are incrementing. So the input, in this case, is the x0. So the input, so the input k, the input 0. So the less significant bits times to E2. E2 is, well, at the beginning is 1, so it's x0, 1. Then we double, though we have 2, and then it's the first bit to the 2. We double the first bit to the 2 to the 2, the second bit 2 to the 3, so to 8, 16. So we are putting all them together, and we are just creating this linear combination. Linear combination is a variable, okay? And this is important that because when you are building circuits, we have this is important because we are building two things. One is what we call the construction phase, and the other is the witness computation phase. In electronics, this is very simple. This is very easy to understand. In the construction phase, mainly we are in the factory. We are putting all the components together. We are just building the circuit. We are just putting the static parts. We are putting the comparators. We are putting the so we are just creating the constraints. Okay. And the other in the witness computation part, mainly what we are doing is we are computing these witnesses. We are computing the specific values. Which values have each wire? In this case, it's not a binary wire. It's just like an analog wire. It's a finite field wire. But we need to compute all these witnesses. We need to compute all these intermediary signals. Okay. So as you can see, there is these two processes. The Circom has these two processes. The first, it runs and it computes the things. And when we are running in the computing the things, the signals, we are working in algebraic form. These signals, we don't know yet which is the value. Okay, so we can build these linear combinations. And mainly, it's a linear combination. It has a signal and a factor for each signal, so it creates a linear combination of that. Okay, so we are creating this in the LCs, this linear combination where while you are adding signals, in the construction phase, while you are adding signals, it does not. So it does not. It just remembers what it is. It just takes that this is a linear combination of these signals with this factor, this signal with this factor. So we are generating here. LC is this linear combination, and at the end, what we do here, well, we compute. In this case, we already compute a signal that's this linear combination, and here all you see here, this is the sine part. Okay. So here mainly what we are doing is we are creating this output, so this output, but we are taking, so we put it positive if the sign is positive, and we just multiply by -1 if the sign is negative. The sign is the most significant bit that you see here. Okay, so we are just taking that, and if this is 0, this is 2 times 0 is 0, so this is just multiplied by 1. But if the sign is 1, there's 1 minus 2 is -1, and multiplied by LC is a linear combination, and this is the result. So here is where actually this constraint is built. We are assigning a signal and putting a constraint. We can do that because here we have only one multiplication. The thing is, in a constraint can only be one single multiplication, and of course it cannot have strange things. It can only have additions and multiplications. It cannot have I don't know, square roots, or it cannot have shift lefts or comparations or something like that. That are the rules of writing circuits. Okay, so we are computing that for mainly what we are doing is we are computing that for each signal. Okay, so this is the first step for all the operators. We are creating this field, okay, that we already have all the inputs, but converted not to a binary, to a field representation. And then here, what we are adding with the LC out is mainly we are just accumulating. Mainly what we are doing is we are adding, but in the field space, we are adding all these fields, okay? So here we have a single constraint that's here, okay? So once we have this constraint, well, what's next? Well, what's next is mainly what we need to convert again to binary, and for doing that, mainly we are just forcing that each of the bits is binary, and as fast and because the number of bits that we are using is less than the field, it needs to hold the constraint. If it goes over, then it will not be possible to convert to a binary, something that's bigger than that. So here there is no danger of overflowing in this case. All these things that you see here, well, this is mainly how you once you have the output, you need to put also the sign. Okay, so the sign here you see something that's interesting in something that's interesting in Circom. Okay, we're using here a single arrow. Single arrow, you should not use it as far as you know exactly what you're using. This is unsafe to use unless you know what you are doing. Here, what we are doing is, okay, we are assigning the sign directly. Just we're putting the sign here. We have this operator here that actually do the work. If the result is less than 0, then the sign is negative, and if not, it's positive. Okay, but we need to also create the constraint. Well, here the first part is that that this field must be binary. Okay, so this constraint, it forces that this sign is either 0 or 1. It cannot be other thing else because of this constraint. Okay, but it can also be wrong. Okay, but the thing is that the nice thing is that if the number is because then we are just, here is the output. We'll see how is the output here. The output is we are just generating the output here, and again we are forcing that the output is binary, 0, 1. Okay, so we will be able to construct this field. We will be able to construct this output if and only if the number is below the number of bits. So we can because this has only an intermediate, so it has a specific number of bits, and it's much less than the total. It's less than 256. In this case, maybe, well, in this case it's 56 bits, so 55 bits. So we need to, the addition needs to fit in these 55 bits. If it does not fit, it will not match. So if we have an overflow, for example, this is not going to work. We are not going to be able to generate the proof. okay? But if it's negative, that means that it's going to be a lot of bits that are going to be also set in there. So we will not be able to put it. So here we need to choose the right sign on the output here in order for this to be able to convert that to binary. So we convert that to binary. So this is how we handle the sign. Okay, so here we just generate the output, and then at the end, it's just we just do the final assignment. We just take the n-1 and we put in them together. Okay, so here you can see quite complex. This could be typically in a library for writing floating points. Okay, you can use the same technique for doing multiplications, for doing additions, well, for doing anything else. So let's go a little bit. Let's go. Let me just move to the original project. I wanted to build it from scratch, but that's maybe it's just better to just. Okay, so here we have, well, a lot of things here. Okay, well, here, this is the main circuit. This is the most important. Here, the only thing that does, it just instantiates with these specific numbers the distance prover that we just created before. Okay, so we have the distance prover here. And then we have, if we see here, for example, we have the, well, floating add, floating multiplication. This is the same from multiplying to inputs and an output. In this case, it's just to multiplications. And we have other fancy stuff here just for adding with a factor. So adding with a, we have a lot of floating point operations that can be built in here. Okay. So, and maybe the most interesting thing is how we compute the distance. Okay, because at the end we need to compute the distance. Well, in order to compute the distance, we are just using this this formula. Okay, this formula is just, well, it's an approximation. It's not the exact distance, but it works quite well. Okay, so here mainly what we are doing is just converting the Earth in a square, in a flat Earth. The thing is that the latitude is very easy, because, you know, it's just from -p to pi, okay, and whatever latitude is, that's the y-axis, okay. And the longitude, the thing is that well, the Earth, it have different diameters depending on what's the latitude. And in the North Pole and the South Pole, the diameter is 0. In the equatorial is 40. So here what we are doing is just correcting the x by the cosine, the cos of the average latitude. Okay, so if we are in the pole, cosine of 90 degrees is 0, so the x is going to be nothing. Okay, but if you are in the equator, then a little angle just moves, meter just really moves a lot of meters. So we are just taking x and y, and then we are just applying Pythagoras here. So this is an approximation. That's what's called equirectangular approximation. It gives a quite good approximation. For our example, is more good than enough. But the nice thing of this is that this is the operations that are here are quite easy. Here we see, well, here we have multiplication. This is the, well, this is a subtraction. Subtraction is the same as an addition, by just changing the sign of the second operand. So we know how to do that already. Here, well, we have a square root, but we need to just prove the inequality. So what we are doing here is just we are squaring this function. So we have this square must be equal to r squared times x squared plus r squared y squared. Okay, so mainly, and then if we just subtract this, if we are just subtracting the left side with the right side, if we are subtracting the and we get a negative value, that means that we are close to. If we are getting a positive, so mainly what we are doing is we are just subtracting the squares. And if we are negative, so we need, with this, we just avoid to do the square root. So that's the first difficulty that we do here. Okay. And the other thing is the cosine. Well, calculating the cosine, it's a little bit more complex, but we can do that inside the snarks, and we just do it by applying the Taylor theorem. Okay, so we just decompose that. It's, of course, it's an approximation, but with 3 terms, we just calculate x squared, x to the 3, x to the 4, and we just compute this cosine. You can see, for example, the average cosine. Okay, so here mainly just takes 2 angles, okay, and gives an output. And here it calculates x squared, okay, so mainly just do an addition and squares the 2 inputs, okay. Here it calculates x to the 4 just by multiplying x squared times x squared, then x to the 6, then multiplying x squared to x to the 4, and then just doing an addition with a factor. So we are adding, well, we have 1, here is minus the first element plus this element to this element. This is the float factor add. That's what it does all together. So it just takes the, in this case is 3, it takes 3 inputs, floating point inputs, and it just adds just the first times the first factor, which is negative number, the second times this this number plus the third times this third number, okay? And these are just constants. These are factors. This is not just a scale. There is the 1/2 because we are doing the average, so it's x plus y divided by 2, and these are already taken into account in these factors. So the output of this just gives a cosine, but with, well, quite few multiplications. Each multiplication, it's about 60 constraints. So we can do a cosine of 56 precision numbers with maybe less than 200 constraints, which is not bad for this. For example, the EDDSA signature, it takes 4,000 constraints, which is, for example, much more than that. Okay, so you can see this modularity, and you can see how we are building all these together. Okay, so okay, we have all this circuit. Okay, and what we do with this circuit? Okay, well, in order to work with this circuit and to plug it in our project, well, the first thing that we need to do is compile it with Circom. So let's do that. Okay, so in order to compile with Circom, let's just well, we just compute Circom. Then the circuit is distance prover main.circom. Okay, and here, and this is the thing, something that's new in this version of Circom. Before, in the old Circom, we just generate a JSON file. Okay, right now we generate many things. One thing that we want to generate is the R1CS system. This is a specific file that just includes all the constraint system itself. Okay. The second is going to be, the second thing that I want to generate is W. It's a WASM. In this version of Circom, we generate a full WASM package, fully optimized, that actually do the witness computation. So from this circuit, we will have just a package in WASM that will compute all the witness, all these intermediary values that's needed to create the proof in SNARKs or in any other, or in many other zero knowledge systems. Okay, we can also generate the S from symbolic. This is mainly just it helps to debug. It mainly is a text file with all the names of the signals, so we can well, we can check. Debugging circuits is very much like debugging electronics. So mainly you just run the circuit, and then you can go with the oscilloscope and just check each of the signals, what are the values. So you can run to the circuit and say, okay, this value is this, but then I do this operation, go to this. But it's more a static thing. It's more like plugging an oscilloscope more than just going just like a normal program that you are just tracing it. You can do that also, but you know, this is the normal way of debugging this. Okay, so minus V, that's verbose stuff. Yeah, well, that should work. So let's do it. Okay. verbose. It generates a lot of tracing things. So here the number of constraints and a lot of things, and that's it. So here now I have if I see here, well, I have a lot of things here because I already ran it before. But here, what I have, you need to just check. You need to see just all the Circom stuff. Plus here we have distance prover.cpp. So this is a C++ for generating the witness, but we have also the WASM part. We have the symbolic, and we have this R1CS. Okay, so this is what this Circom generated for us. Okay, so if I want to run a snarks, then I can go to a snark.js, and the snark.js I run the setup. I already so if I do the snark.js, well, as R1CS, you need to hear is was the distance prover mine dot R1CS. Okay, so this is the R1CS system. Okay, well, it's not JS. I want to run the setup. JS setup. Okay, by default, now it just take growth 16 as the standard one. So I just generate it. Well, this may take a while. Just running the setup. This is well, you can run. It's better maybe to run the setup maybe with Bellman or with other libraries that go much faster. Snark.js is just for playing and for working with a small circuit. Okay, and this setup would generate mainly two things. The proving key and the verification key. The proving key is mainly all the information you need in order to generate the proof. You can see here that it was already generated before, and the verification key. Okay, that's mainly what you need to verify the circuit. The proving key is a big file. It's quite huge in general, but it depends on the number of constraints. But it used to be a big file. Generating the proof is very hard in the snarks. But verifying is very cheap, and the verification key used to be very small. Depends mainly on the number of the public inputs or public outputs, but used to be just a very small file. So the verifier in general can run easily. Actually, you can run it even in the blockchain itself. Okay, so here I want to introduce now what's running the setup. That there is another package that, well, it was called before, WASM. It was called before WebSnark, but we just renamed it to WASM Snark. It's exactly the same project, but what actually does is just computes the proofs and verifies the proofs in the browser, mainly with WASM. It's a very highly optimized WASM library to run, to compute the proofs and verify the proofs. Okay. And another thing while it's running this that I want to mention, and this is the new things of the Circom, is that well, it also all the C++ that generates is very optimal. Actually, there is a library that we created. Let me just show for you. GitHub.com. Let's see. This is FFIOI. This is a finite field library that works directly in assembly. This is very fast, and is used together with C++ generated. We will generate it now. And mainly what it does is a library. Let me just show you what it does. It just take a format that looks something like that. You have, when you see a number, a finite field number, you have the, what would be the, well, you have this, okay? The first thing is that you can have the long representation or the short representation. If you are working with small numbers, you are using the short representation. So we have a flag here at some point. That's this is the most significant bit of the first 64 word, okay? That says if it's long or short. If it's short, it takes this side. If it's long, it takes this side. And the other flag, it says if this side is Montgomery or not Montgomery. So you can have a number that's short and Montgomery. That means that this is the short representation and this is the Montgomery representation. You can have a long normal. That means that this is just a short, it's skip it, and you just work with the long side. And long Montgomery means that this side is Montgomery. And the idea of this library, it's an assembly library that just takes the inputs, and it takes in account if it's long, short, Montgomery, non-Montgomery, and it does the best thing in order to compute that. So for example, it can compute, for example, short times Montgomery, long times long Montgomery. So it takes all the possible combinations, and it computes that very, very fast. And this is for computing the witness is very, very interesting because it goes really fast. And this exactly the same library or the same format works with, we have like two libraries. One is for Intel assembly, the other is for WASM. And it uses exactly the same format. So the witness computation that you generate in Circom, it can be run in both things. Actually, and it could be very easily to export also to other languages like Golang or maybe Rust or other languages. It could be very easy to for Circom to generate code. For example, in order, the same way that I'm generating C++, it could be possible to generate Golang or Rust or any other language quite easy. It's very much prepared. It's not done yet, but it's prepared to run for to be integrated to any language. Also, another interesting thing is that the witness computation in Circom can be run in parallel. The idea is that because these are components, and these components, you know, they work. It's like an electronics. They actually can work very much in parallel. So there is like a all this C++ code actually runs in parallel. So if the circuit is well designed, because you may have some dependency things inside, but if you don't have dependency, that there are some tricks to avoid these dependencies. You can run this witness computation in parallel, and it goes really, really fast. This is, for example, in the rollups is very important because this was one of the bottlenecks that we had, and it's not the bottleneck right now anymore. Okay, so that's the thing. Other things that are interesting and I wanted to show here is, well, these numbers also, you see, works in positive and negative. A lot of times the witness, you see the negative also are short. That's not an important thing on that. Maybe the other thing that I want to mention is that it works with any core. It does not only work with BN128, that's the original core that we were using, because the one that's used in Ethereum, but right now the Circom is time field agnostic, so you can work maybe with MNT cores, or can work with zkSummit or any other core with that. So, well, let's go to the project. I don't know how I'm going in time. It's well, it's a little late, but yeah, I'm continuing. I'm gonna go. So it just if anybody wants to leave, I'm just continuing the stuff. It's a lot of people here, by the way. Let me just do a little 30 seconds of break. Oh, not bad. It's a lot of people still. Okay. Well, let's continue. We already created the setup here. Okay, so we have already the setup. So right now, well, we already have an input example here. So let's now now we need to run the witness computation. So to run the witness computation, we just do a snark.js. And we want to use the WASM file that generated before. Then the input, it will just take the input.json. That's the input of the circuit. So it will compute all the witness of the circuit given the given input. Let me just, I think it's -i. Input.json. And well, this is witness.json. Actually, it can generate JSON or binary, but I'm generating here JSON, and yeah, that's mainly it. So this is just it's not computation; it's witness calculation. Well, just generated the witness JSON, just all the files. Some of them are 0, which is normal. Okay, so this is just the witness computation. Okay, and now just once we have the witness, have the setup. So with the proving key, with the witness, we can now generate the proof. Okay, so we can do, for example, Snark.js. Okay, so here is the, well, we can, by default, it takes the public the same name, so I just avoid the parameters, okay? Just, this mainly takes, you know, the witness, takes the proving key, and it computes the proof, okay? Proof, it takes a while. We'll see that later when we run it in the browser. It runs much faster, because here we are just using this Snark.js, which is not optimized. It's just for playing around. But if you want to run it, then it's better to go directly to the WASM Snark. That's much more optimized. Let's open another window. Well, it's already done here. If I verify, should say okay. Okay, so I generated a proof, the JSON. This prover also generates the public. This public, this is the identifier, and this is the packet reference. Okay, so these are the two public inputs of this circuit. Okay, so we already have this circuit. We can test it here. We have it in command line. So how we do that? How we work that in? How we work that to our project? How we connect to our project? Well, as I told you, we are using WASM Snark, okay? That uses exactly the same formats and everything than here. So in order to have the WASM Snark, let me just see how the prover works. And just go to the source. We see the prover. Well, okay. So here you can check it, but here the prover. Let's see what the prover does. Okay. So in order to do the proof, here mainly what I do is, okay, I have the signet position, the reference, so I get all the mainly. First thing is all these reference parts. I just pack them all together to a binary. This is a reference. Okay. So as an input, and here I construct the input to the circuit. Okay. So the input to the circuit is just well, the reference that I built before. I have here the position. Well, as an input, I have the, so I have the position. The position is mainly what was signed by the signer. Okay, so here I just take what it was. We take as an input all these. As an input, we take all this signer position, and that mainly is the packet field with the signature and all together. So here I just extract here what would be the message. So I extract here is the position. reference. Well, we build the position, that's what we built, and then we extract from the we extract from the buffer position, we extract the signature. We put the reference, and we also put the position. What the hell is this? Oh yeah, this is the first element. This is the first element of the first field element of the position. The second and the third are the signature, and the fourth is the S. So this is from the position. What signed it, we have the original. That's what we call the position here, the message that's signed it, and the signature here. And then we have the reference. And with all that together, well, we print it here. This is interesting to print it because then I can cut and paste to the input file somewhere. Okay, and here is what's interesting. Witness calculation builder. Okay, so where did this come from? Well, this is in order to work with the WASM. Okay, so the WASM we just load at the beginning. We just fetch it here, depending if we are in Node or we are in the browser. We fetch in a different way, but here we are just getting all this. Mainly what we are doing is just getting this WASM as a buffer. Okay, and we pass to this component is the witness calculator. The witness calculator is included in a repository that we split from Circom that we call it Circom runtime. By the way, Circom runtime, so Circom is GPL license, but Circom runtime is Apache license, so it can be used so the Circom programs can be used everywhere. So this is a split in well, it just take it in here you see here in the Circom runtime is the witness calculator, and this just takes care of just as an input, it takes the WASM. Well, you see here how it works. Just create this just witness calculator builder. We build out this witness calculator, and then the witness calculator, we just pass the input. That's what we construct here with the inputs of the circuit. Well, here we have an option, we put a sanity check. Mainly we double check that the constraints also fulfilled. This would not be necessary in a production code, but this gives also some information if something goes wrong in here. And then the results of witness. With the witness is just an array of all the witness itself. Okay, so here what it does, all this stuff here is it packs that to a buffer. This is we probably are going to improve this a little bit because the problem here is that Node and the web, it works a little different with buffers. So you need to do some tricky things on there. So if you're using here, you can take this as a reference of a way of converting. We're probably going to simplify this stuff, but we are converting all these witness to a buffer. And then we are just using the BN128 that actually is the BN built BN128. This is the web snark, the WASM snark. So in WASM snark, the way to use WASM snark is mainly we have this build BN258. In the init code, we just build it. Okay, so we have these extensions of this BN128. And then we just call BN growth 16 hand proof is generate the proof. We pass the buffer, okay, and this is an array buffer, okay, and the proving key, okay. The proving key, it's also well, we get it from the setup, okay. It's just a normal buffer too, and that's it. And with this, it just generates a proof, and we just output the proof. If we see that, let's try to do this in here. Okay, let's go here. Okay, so if I just take this signal position, this is what gets from here. I put it here, okay, and I want to prove that I'm less than here. Here is exactly the same position, so it will go. Oh, I do not have. It's trying to load the proving key, and it's the server is stopped. It took so not. Let's just reload that. Let's do it again. Now we load it, and you see how fast it was. It took like 1 minute or so. And now we do it here in the browser much faster, because this is right and full in WASM, and the generation of the proof is much faster. Okay, so well, and now that we are here, we can just take the proof and verify that. So the input, we have the verifier, we put exactly the same identifier, the same reference, and all that together, we verify it and say it's valid. You see that the verification is also really fast. Verification in the snarks is really fast. Let's see for the last, let's see how a little bit how the verifier works. The verifier you can see here. So mainly what we are doing is, well, we are building exactly the same component, the BN128. Okay, we have the reference. We build the reference from we pack the reference as we see before. We construct the public key. We have this, the identifier and the reference. And here we just verify that. We pass the verification key. That's load here is a JSON file. It's very small. Okay. We have the public key, which is this, and we have the proof. The proof, you see, it's a JSON file with just the points of the corp. So the verification key is exactly the same WASM snark, and you can verify that in the browser easily. Just to show also how the C++ code work. We generated the C++, okay? So in order to compile the C++, in order to generate the witness computation of the C++, well, the first thing that we need to do is we need to build this finite field library. So in order to do that, we just yeah, we build this comment. So mainly is, well, here we are running this in the module finite field IASM. We build this build zkfield.js. Actually, what this library does is it's a JavaScript code that generates Intel assembly. Okay, so it's a template, and this Intel assembly, you as a parameter, you give the prime number. So it will generate a very optimized code written in assembly with the Montgomery multiplication. So all the possible optimizations done, it will be in assembly and will generate an assembly file. Okay, so when I run this, okay, what it does, it generates these files. This is what we call fr.asm. If I see, for example, how this would look like, you see this is an assembly code. Okay, this is generated by this library, and you see here there are all the operations that work in this finite field. Of course, you have addition, multiplication, but you have also shift left, shift rights, binary operations, have all sorts of operations, because Circom needs it in order to compute the witness. So it generates this assembly, okay? So I know that I have already the assembly. Well, the next is I need to compile the assembly. In order to compile this assembly, I just use NASM. So you see NASM, in this case, I'm in a Mac, so I'm using this. If you are, well, if you've seen the README of this finite field library of the FFIASM, the documentation is there, okay? But here, this is very specific for Mac, okay? So, but with this, mainly what it does is generate an fr.o, okay? It's an object file. So know that I have this, so we have right now, well, I did it here. Well, I wanted. Well, I have the fr.o that's generated by the assembly. Okay, so now that I have the finite field library that's already generated. I have the C++, the Circom, what generated the Circom. Okay, and then I plug them all together. And here I run this. What I have here? Well, I have of course, the output of the Circom. I have the finite field library. There is also this script also generates a fr.c. This probably is going to be removed in the future, but there are some not very much used operations that is using the GMP still. They are very strange ones, and we will remove all of them so that we don't have this dependency yet. But right now we have this frc.c still yet, because there is still some of the very rare and difficult to implement in assembly that still uses the GMP. But there are now exponentiation and some very strange things. Okay, so and then here we have all these calculate witness, the main, and the utils. This is everything is in the all this is in the Circom runtime. So in the Circom runtime, we go to the Circom runtime. Just let me go. Let's see. Show you. Moment. If you go to, you see the Circom runtime. You have all the runtime for the C. You have the runtime for JS. On the C, you have these C++ files that you need to build this C++. So it's actually what actually is the common part. What actually do the main and you know all the computation there. So the output is going to be called distance prover.main. Well, we need GMP because we are still using something. This is not be required. We also say that we also include the point. Just here is we are telling the compile where to look for the include files. So we just run this, and this generates just generated this. So I can already run main, and as an input, it's input.json. It could also be, it accepts two kind of inputs, JSON and binary. In this case, I'm using JSON, but it could also use binary. And then I just put witness.json. Okay, so this just runs the witness computation, and you have all the code here. Of course, it just compiles, but maybe you want to embed in your application somewhere. Okay. So here, just generate. You see how fast it works. You know, it takes more time just to load the same program that just to compute the witness itself. In this is the small. Okay, so I have this one still have all the, well, it's exactly the same because I'm using the same values. Okay, but you see here also as a tutorial a little bit how to generate this C++. Okay, so we have run all together. So we have all this system. This system is working. This is of course, it's not a production. Well, this is it's an example project, but that's mainly what I wanted to show in this workflow. All this, let me just share with you the GitHub repository of this. Everything is in the IDEN3 project. If you've seen the repository in IDEN3, there is a lot of things related to zkSummit snarks that are interesting. Here is this is called distance prover. Just go to IDEN3. Prover. Have everything here. All these. Just let me just, if I see the chat, I should. How do I? Can you? I don't know if anybody. How do I? How do I unshare my screen? This is Zoom. How do I stop sharing the screen? Stop video.
There should be a button like to stop sharing. Just keep looking whether
Oh
there's
yeah,
any.
here, just to stop sharing. Yeah, here is stop sharing.
Yep, there should
Okay,
be a
got
button.
it, got it, got it. Okay. So let's see. Just let me cut and paste. This is, I want to go to the chat. Just here is the moment. Chat. Okay, this is the link of the repository, and also if you go to Telegram, let me just share the IDEN3 Telegram group. If you have any questions in that, this is an amazing channel. So every doubt you have in Circom or anything that that you're interested or whatever, this is a quite good channel. Try to keep it as less noise as possible, but IDEN3 just copy link, yeah. Okay, here go, chat. This is the Telegram group of IDEN3, and well, that's it. That's what I wanted to show, and please feel free to contact me or anybody in this group. It's amazing people there. So thank you, that's it.
One moment, are you guys seeing the link to the chat, or it's just me? Like the link to the Telegram group? Oh, it's over there. Okay, I was a little bit slow. Thank you, Jordi.
I don't know if there is any questions or anybody wants to ask something.
Jordi, it's really good to see that the libraries come together really nicely. What's the benefit of the rank 1 constraints that you get as opposed to what you used to get before? And does it help, or what can we use it for?
Well, R1CS, the idea is to R1CS, for example, the first thing is that's much more compact. It's in binary, So if you work with big circuits, going with a JSON is not viable. If you are talking about in millions of constraints, you need to go to binary for sure. So that's the first thing. The second is that this is much more. Well, it takes less to load. It takes less to transfer from one side to the other. It's much more manageable. And this binary, the idea is that it could maybe make sense maybe to plug it in different places. For example, you can take this R1CS and maybe plug it to another language. So just import one component from one language and put it in the other, and just start to mixing things. So that's it's not possible yet, but that goes in that direction. So here, and also because before in the JSON you had these constraints, and you have also the a JavaScript code that just generated the windows, but was really slow and very bad. And it was everything mixed. So here it's very clear. It's like the constraint system goes in one side. This is what's needed in the setup, in the trusted setup, and you can export. Maybe you can go in one direction, and the other is the witness computation. And this is these are two parts of the Circom. Circom generates these two things, and we keep it separate, and it makes a lot of sense to go in one direction and the other. You need the WASM to compute the witness or whatever, and you have the constraint system and generates the two things. That makes more sense.
Yeah, perfect. Thanks, Jordi.
Any more questions?
Do you plan to implement any other proving system except gross 16?
Yes. Let's see when we have time, but I want to, here there is two proving systems that are at least in my list. One of those is Plonk, and the other is Bulletproofs. These are the two that at some point would make sense. But the nice thing is, because these are R1CS, you can plug it. Actually, there is also some plug, for example, with Bellman, and So it's not difficult. The way it's done, it's not difficult to plug it in any circuit, because you have right now, you have this split pretty much, because you have this JavaScript, this witness computation in one side, you have the constraint system in the other, and you can pass that to any other constraint system. So it's just a matter of developing and pushing. But what's in the to-do list is this, plus I want to start working also in the pairing component, right? In the Circom, that are the things that are in the plan. Let's see the order and the priority, but that are the things that I would like to do at some point. More questions? Okay, guys, so I think that we are done. Thank you very much for being here. Let's go to the conference.